Hello everyone, welcome to this tutorial. So in this tutorial I'm going to show you how to download and install and set up the GNSS SDR Toolbox for MATLAB. So the first thing you want to do is go to the website and download this version 2.06 of the toolbox. And then you also want to go to this data file section, go to this FTP site and download the data files that are available there. So today in this tutorial I'm going to show you how to set up and run this 3NGS um, data files. So that's coming from this RF front end that you can purchase from Spark Fun Electronics. So here's the link right here. So what you want to do is download the data file from the FTP site and then download the meta file from here and make sure that both of those files are in the same directory. So I've got them here in this path over here. The meta file is actually an XML format file that shows basically tells the software radio toolbox how to extract the binary data that's within that file, and then also has all of the front end parameters like the number of samples per bit, sampling rate, the center frequency, and the IF frequency. Okay, so then also the other thing you want to do is the toolbox is a zip file. You want to unzip that, and here I've extracted it to the C drive. So you see these files and three directories. So after you do that, you can also see that there's a getting started guide that you can read, which pretty much has all the information that's in this tutorial. Okay, so the next step is go into this mexw32 directory, and we'll be generating all of the PRN code files by running two applications. So the first one is this bat file, which is going to take all of the hex strings um, that represent the Galileo PRN codes and then convert that over to a binary file format that the toolbox can use. So you do that by running this batch file. Okay, so that generates all of the Galileo memory code files. And the next thing you want to do is run this LFSR code generating executable. So this will generate all of the PRN codes for GPS, L1, L2C, L5, Galileo, and Beidou and GLONASS as well. Actually, take that back, not Galileo, but GPS, Beidou, and GLONASS. Okay, but after you're done, you should see about 1400 different memory code files in that directory. And so the toolbox is going to use those files uh, inside the correlation engines. Alright, so the next step now is to open up MATLAB. And I'm going to browse, go to this path here, and you can see the files. And so the next step you want to do is include the libraries in MATLAB's path. So if you have a 64-bit machine, you should include this directory, or if you have a 32-bit machine, you want to include this W32 directory. So I'm going to include the include directory and the W64. So right click and say add to path selected folders, and to make that permanent, every time MATLAB opens, you want to go here, file, set path, and just say save and close. Okay, so now that's set up. So to get started, we are going to do some acquisition of GPS CA code signals. So you open up this quick acquisition CA, and you want to make sure that this SDR file variable is a string that's set up to the file name that you downloaded from the website. And then also the paths CSV, that's a comma separated string that shows all of the paths where the toolbox will use to look for data files. So this script is going to search through PRN 1 through 37 and 130 through 140 for signals. So let me run this. And when it's done, it's going to find 8 PRNs, 6 of which are GPS satellites and 2 are SBAS, VAS satellites. Okay, so when this acquisition script runs, it actually generates a pointer file that the tracking program uses to find the information to pick up the acquisition parameters. Let's do the same thing for Galileo E1. So run this quick acquisition Galileo E1 script. It should be all set up to run as well. So here we are going to look for PRN 11, 12, 19 and 20, because those are the 4 PRNs, Galileo PRNs that are out there right now. So we run this. If we expand this correlation function, you can see the typical BOC11 magnitude correlation function with the 3 peaks. Okay, so now we are done with acquisition. So let's go to the tracking function, so which is GNSS track. Open this up, and so this script is set up to track all of the signals in the different data files. So make sure that this if statement is true for this GN3S, which should be the default. So again, the SDR file variable is pointing to the file name. The path CSV is pointing to a string that's comma separated where the files are stored. You want to start the block where you want to start tracking from, the number of blocks you want to track. So let's expand this to, I'm going to go to say 110 seconds. The user call function that stores all of your universal tracking loop configuration is in this file, and this run sets is a listing of all the state transition matrices, which is actually in this file over here. So if you go through this file, it has all of the state transition matrices for the different signal types, and I'll have a different tutorial that explains all of this. So the way you set up channels is through these columns. So you have a signal definition string, a PRN number, the stream index where that particular stream of data is stored in the file. So you can have multiple data streams in the same file. In this particular file though, there's only one data stream, so it's stream number 1, and then the run set index, which is basically the index of the state machines. So you can have any number of columns, as you can see from this example over here. So here it's actually set up to do 7, actually 6 CA code satellites, 2 Galileos, and 2 VARs. But for this tutorial, I'm just going to run this one here for 110 seconds. Okay, so basically that should be all set up. So hit go, and it's going to track this one satellite. You can see the report over here, and it's going through all of the state transitions. While that's running, let me open up the task manager. So this PC is a dual core machine which has hyper-threading enabled. So you can see 4 logical processors, and they're all busy doing the correlation because the toolbox is targeting multi-core processing. So let's allow this thing to complete the tracking for 110 seconds. Alright, so it's done running, and so it basically took about 261 seconds to run a 110-second data file. So basically roughly 1/3 of real time. When it's done running, it actually shows you where the results are stored. So this path over here. So if we go to this output path, you can see that there's a folder with a timestamp. If you go into that, there's going to be 3 files in this case. So it copies the acquisition file so that you can have a look at what acquisition settings were used in the tracking. There's also a transcript which is showing you pretty much everything that was displayed in the MATLAB console window. So all of the state machine settings and everything that you would ever need to know about this tracking run is included in the transcript. And then also finally there's this SGF file which is going to contain all of the tracking outputs. So things like the NCO commands and the raw correlator outputs and the measurements are all embedded in this binary data file. So the next thing we're going to do is open up that file and plot the outputs of the tracking run. And we do this by running this track plot program, or script rather. So this script is set up to uh, pull the SGF file using 2 methods. The first one is, given the name of the data file, it will pull the latest tracking run, which is what it's set up to do right now. Alternatively, you can actually point to the SGF file directly. So this script is also showing you how to pull data from those SGF files. So right now it's set up to pull data for channel number 1, which is all we have, and the entire range. So I'm going to go ahead and run this. And when it's done reading, it will generate a series of plots. Alright, so let me explain this. So figure 1 is showing you the state transitions up to state 14, which is the final state. Figure 2 is showing you the raw 1 millisecond integrated correlator outputs. Figure 3 is showing you the phase, the arctangent measured from the 1 millisecond integrated prompt correlator. Figure 4 is showing you the states of the carrier tracking loop. So this is acceleration, velocity, and range. This is figure 5. It's showing you the same thing for the code tracking loop, but because it's aided by the carrier tracking loop, you don't have acceleration and velocity states because it's a first order loop. Figure 6 is showing you the range measurements, and in the final state, once everything has settled down, I reset the measurements, the carrier and the code. By the way, this is the code measurement is just uninitialized. So they're both set to 0, and that allows us to see code minus carrier with a 0 starting bias. So you can see that after it has settled down, this is what the code minus carrier is looking like. So because this tracking function is tracking at 0.01 chip correlator spacing, you get very low noise code measurements and multipath as a result. Figure 8 is the phase lock indicator, where value of 1 means that it's phase locked. This is the 20 millisecond integrated correlator outputs. So we are actually running a double delta correlator in the last state. So you can see that we have 5 correlators: prompt, early 1, late 1, early 2, and late 2. But because the correlator spacing is 0.01 chips, all of those are very close together, as you can see over here. Figure 10 is showing you the pre-detection integrated correlator magnitudes, and I believe this is 200 milliseconds of coherent integration that's used to drive the coherent code tracking discriminator. So again, you can see how close together the points are. This is the frequency discriminator, which is turned off after we go to PLL mode tracking. This is the phase discriminator, and these are various correlator outputs for various code discriminator non-coherent implementations. The final one that's interesting here is the code discriminator for the coherent double delta discriminator. So because the correlator spacing is 0.01 chips, you can see very low noise on the code discriminator output. So it's down to, the noise is around 0.02 meters, which is 2 centimeters or so of standard deviation over here. And then the final plot is the carrier to noise ratio. So this is a very strong 50 dB hertz type signal. Okay, so with that, this concludes the first tutorial, and I'll be having other tutorials that go into more depth of the GNSS software defined radio toolbox for MATLAB. Thanks for listening. See you next time.